Go back just a few decades, and you'd find these spinning metal domes on warehouses, barns, and residential rooftops across the United States and Australia. They're called turbine ventilators, or whirlybirds. Independent testing has proven that these unpowered spinning vents can drop peak attic temperatures by as much as 37 degrees Fahrenheit. That translates to cutting a home's cooling costs by nearly 15%, all without using a single watt of electricity. But if you walk through any new housing development being built today, you will struggle to find even one of them. So if a device can consistently slash utility bills by 15% using zero power, why did the housing market abandon it? And looking at the data, should we actually be bringing it back? To understand the specific problem this invention solves, you have to look at how a roof behaves in the summer. Solar radiation bakes the exterior shingles, turning the enclosed attic space into a massive thermal reservoir, where temperatures regularly climb past 150 degrees. That trapped heat doesn't stay in the attic. It radiates downward, bleeding through the ceiling and into your living space. This actively fights your home's air conditioning system, forcing it to run longer and consume more power to maintain the same temperature. This chart shows exactly how much that thermal bleed costs you. According to the Department of Energy, every single degree of attic temperature increase boosts a home's cooling load by up to 4%. In 1910, an engineer named Samuel Euckert patented a clever solution to deal with this trapped heat: a spinning cowl that sits at the very peak of the roof. The entire objective of his device is to intercept and continuously exhaust that thermal reservoir outside, eliminating the heat before it can cross the ceiling and cost the homeowner money. The baseline performance of Euckert's invention is highly efficient. A standard 12 to 14-inch turbine can move up to 500 cubic feet of air per minute when pushed by just a 5-mile-per-hour breeze. It achieves this by relying on Bernoulli's Principle. As normal wind strikes the curved outer vanes of the turbine, the air is forced to accelerate. In fluid dynamics, when air speeds up, its pressure drops. This creates a low-pressure void inside the housing. That void acts as a vacuum, sucking the trapped 150-degree air upward from the attic and exhausting it into the atmosphere. But the system relies on a second principle for the days when the wind stops entirely. Because hot air is naturally less dense than cold air, it rises on its own. This creates a gentle pressure gradient, known as the stack effect, that steadily pushes the heat out through the top of the stationary unit. So even at a complete standstill, a turbine doesn't act like an open hole in your roof. It serves as an exhaust cap, specifically shaped to leverage the natural buoyancy of heat. There is a third physical principle at play here, the Venturi Effect. As the stack effect and Bernoulli's Principle pull the hot air upward, that air is physically squeezed through the narrow, converging gaps between the spinning metal vanes. When fluid is forced through a stricture like this, its velocity rapidly increases. That fast-moving exit air drops the internal pressure even further, pulling more air up from the attic and accelerating the entire exhaust cycle. By compounding Bernoulli's Principle, the stack effect, and the Venturi Effect, the system creates a self-sustaining multiplier where each distinct physical force makes the other two stronger. Utilizing the geometry of a structure to passively pull air is one of the oldest engineering solutions in human history. Persian architects built tall masonry towers called wind catchers to funnel breezes downward while pulling stale air out the top, long before the Industrial Revolution. Euckert's 1910 turbine was a refined version of this ancient concept. It is a continuous, zero-electricity engine powered entirely by atmospheric geometry. If this device effectively harnesses fluid dynamics without needing power, we have to ask why modern home builders stopped installing them. The primary issue was mechanical failure. The spinning head relies on internal ball bearings. Over time, moisture, dust, and insufficient lubrication degrade those bearings, turning a silent machine into a grinding noise nuisance that echoes straight through the ceiling. Then there is the social limitation. Homeowners associations heavily restrict or completely ban turbine vents because their large, metallic profiles disrupt the uniform aesthetic expected of modern suburban rooflines. Finally, they suffer from an engineering flaw known as short-circuiting. If a turbine is installed on the same roof as other passive vents, The turbine's powerful suction can accidentally reverse the flow of those other vents, dragging outside rain and snow directly into the attic instead of exhausting hot air. The turbine's fatal flaw was never its physics. It fell out of favor because of mechanical friction, a highly visible profile, and total incompatibility with complex modern roofing systems. As codes evolved to require tighter, more energy-efficient homes, the construction industry demanded precise, evenly distributed ventilation, leaving no room for unpredictable wind variables. The solution settled on was the ridge vent. It runs the entire length of the roof peak, capped with shingles, operating with 0 moving parts. A full-length ridge vent provides over 900 square inches of ventilation space. Because that airflow is distributed evenly across the entire roofline, it eliminates the dead zones that isolated turbines create, all while remaining virtually invisible from the street. The ridge vent ultimately won the modern suburban market, but for homes in hot, windy climates, the turbine ventilator remains a functional example of applied physics, an enduring zero-carbon tool for keeping buildings cool.